Thank you to follow up my monologue on our chapter 7.3 regarding the frequency-dependent permittivity on our course in solid-state physics. So what we will do in this lecture is that we will try our best to generalize the concept of a molecular polarizability. And how we want to do that is that we want to include or have a possibility of including now several different physical contributions into the response of the substance on the microscopic scale. So what is the molecular polarizability, so to speak? So essentially these different contributions, they affect the optical response and also the electrostatic response of our material, mainly at different wavelengths. So in essence, what we get out is that we have a wavelength-dependent molecular polarizability that we will be describing in this lecture. And after the brief introduction, the main concepts and what are the main contributions, we will in the section 7.3.1 then describe the harmonic oscillator model or harmonic damped oscillator model. So essentially we will introduce to you a Lorentz model for an atom and an electron. And this, of course, is a model that we have already introduced in our earlier course, especially in our course in optics. And if you don't mind, if you don't mind in having a kind of like a reintroducing this concept, we will go through the Lorentz model in this lecture. So essentially it's a damped harmonic oscillator model, and that gives rise to us a frequency-dependent permittivity. And of course, if we have a frequency-dependent permittivity, then we can have a frequency-dependent refractive index for the material, for the solid. And we end briefly by generalizing this treatment, where we first of all in the Lorentz model, we have a single resonance in our oscillator model. We generalize that to include a possibility of having several resonances. And then the resulting formula will be the Helmholtz-Kettler equation or formula. Of course, this has actually many names, but perhaps the best known is the Helmholtz-Kettler equation. And maybe, depending of course on the year that you are listening this, but we might have YouTube lectures on our course in optics. At least we have a plan of do them during the fall of 2023. And if the year is 2157 now you're listening this, then you might have a availability of those lectures on the Lorentz model already at your disposal. If you don't mind listening my babble in Finnish, they certainly are already openly available, those lectures, but we also have plans to extend our lectures to English regarding our optics course. Just in case that you want to have a listen what I'm describing here from a different point of view, or maybe you want to put that into a different context. Of course, it's a matter of your taste, but maybe it's a relevant piece of information to you in case you're interested. But now let's get started. I will start with the lecture. So what we will do first is that we will go through the very basics. So what we do here is that we will try to elucidate to you the big picture. So essentially we want to describe the material response. And essentially, we want to understand the kind of microscopic material response. And the parameter that describes this is the molecular polarizability alpha. And like we've said, there's actually different physical contributions that affect the strength of the molecular polarizability. So we have many different contributions, and they arise from different processes. So for example, at the very short wavelengths, when we would be speaking of X-rays and gamma rays in terms of photon energies and photons, then we would be speaking possible atomic relaxations and excitations, the atomic core processes, or inner electron excitations. So those very short wavelengths we do not describe here, so we forget them essentially. But needless to say, at some higher energy regimes, you should really consider what happens for light-matter interaction or electromagnetic radiation matter interaction when we have energetic particles or energetic radiation that is hitting our substance. And then in case it's not clear to you, X-rays and gamma rays, although their kind of wavelength regime is not entirely overlapping, you also have a regime where you have equal energies in terms of EVs. for X-rays and gamma rays. And actually for the people who are working with these kind of like highly energetic photons, X-rays, actually the terminology means that they would originate from inner electron excitations and relaxations. And if you speak of a gamma ray radiation, that would actually be originating from a atomic core nuclei transitions. So you would actually have a kind of like nuclear process that excites your nucleus into an excited state. And when that excited state, a nucleus relaxes, then you end up having gamma rays out from your atom. So there's really also that kind of difference. It's not just a distinction between the energy regimes, but also there's a difference between the kind of source of origin, physical origin in the radiation. So when you have gamma rays, those actually originate from the nuclei. We're speaking of nuclear physics here. And when you have X-rays, then you would actually be having something caused by excitations and relaxation of the inner electrons in your atom. So there is this difference, in case you're interested of knowing this kind of bit of information regarding terminology. Now, okay, so we have the molecular polarizability alpha, and we really want to understand this material parameter because it tells us what happens on the microscopic scale for our substance. And this parameter, it really heavily depends on the incident wavelength, what is the strength, and when we go at the very high energies that are incident on the piece of a material, when we are speaking of the extreme ultraviolet and ultraviolet regimes, then we speak of photon energies of the order of 10 to the 124 EVs. And when the incident photons are this energetic, this is an energy per photon, single photon, then what happens is that these atoms that our solid is being formed out of, they are essentially ionized. So that the valence electrons get ripped off out of the atom, and then we will have an ionic contribution into the molecular polarizability. So we will have subsequent resonances and changes into the molecular polarizability due to these kind of processes. But these start happening at the very short wavelengths, so at the XUV and UV regimes. When we reduce the photon energies, so we are speaking of ultraviolet and visible wavelength ranges, we speak of 1.55 electron volts all the way to the 10 EVs. So then what happens is that we will have valence electrons and they get excited into higher electron excitation stage, but they don't yet ionize. And then we speak of electronic contribution into the molecular polarizability alpha. And this is the main contribution when we speak of UV and visible wavelength regimes. So we have electronic contribution, so electronic transitions that affect the light matter interaction. And then when you go to the longer wavelengths, so smaller frequencies, we speak of infrared frequencies, and the EV range will be 0.0 milli electron volt all the way to the 1.55. That's the regime where we stop having infrared radiation. What we actually excite in our system, in our solid piece of a matter, are phonons. So those lattice vibrations that we were describing in our chapter 4. So then the subsequent name for the contribution is lattice contribution. And physically what would happen here is that we would shine infrared frequency into our solid piece of a substance and phonons would be excited. And now we would actually be speaking of those optical branch phonons. If you recall those two different mystical branches in the phonon dispersion relations that we were describing in chapter 4. So we had those acoustic branches and we had those optical branches, and this frequency range more corresponds to the optical branch of phonon vibrations. And then when we go into even longer wavelengths, so at the radio and microwave ranges, we would be speaking of less than 0.0 millielectron volts per photon energies, and then it would be the dipolar contributions that would dominate. And in terms of what kind of physical contribution we would have in a solid substance, we would be often speaking of here of the acoustic phonons that we are being exciting in our system. and that are being affecting how light interacts with matter. So please put it in context that now we have also described phonons, and we remember the phonon dispersion relations, so that we did have the acoustic and optical branches in our dispersion relation. And here, depending really on the wavelength that we are using in our excitation field, we may have a different contribution of different types of phonons. And then subsequently, let's turn this piece of information other way around. If we would be interested in understanding what kind of phonons we have in our system and how they would be in terms of their phonon dispersion relations, we would see that in principle, by shining this kind of radiation and being able to adjust the incident radiation's frequencies, we might be able to extract information of phonons and even information of lattice dispersion relations of phonons, so that you would not need to do neutron scattering experiments, at least in principle. So we have these different physical contributions, and they give rise to a frequency-dependent behavior. So the molecular polarizability alpha, it's not a constant valued quantity, but actually, in fact, it depends on the incident frequency of electromagnetic radiation. And here in this chapter, in this course, we will here focus mainly on the electronic contribution and then on the dipolar contribution. So what happens in terms of phonon vibrations in our piece of a solid. And in order to understand what happens, we will in the next part, we will reintroduce to you the harmonic oscillator model, so that we can understand how the polarizability is frequency dependent, and we can understand the physical origins behind this frequency dependence. So mainly here we are interested in the electronic contribution, so what happens near the infrared regime, so what kind of phonon dispersion relation and what kind of phonons we can excite and whatnot. And then also on the electronic contribution, so what happens closer to the UV regime, that's where we have the electronic contribution. And then these resonances that take place, absorption that takes place in a dielectric medium at the UV wavelength ranges, that affects, of course, the refractive index profile of the substance at the visible wavelengths. So this is a very crucial information for many physicists in optical physics. So this is the kind of like a brief introduction, and on the other hand, a motivation for our upcoming section. So we want to understand what is the frequency dependence of polarizability and what are the kind of physical origins behind that frequency dependence. So now I will start with the chapter 7.3.1, where we will be treating the mathematics that helps us to understand the dispersion of polarizability. And how do we do this? Is that we will briefly reintroduce to you a Lorentz model. So Lorentz model essentially is we assume that we have a single atom, and it's being surrounded by an electron, and the electron is being bound to the atom by electrostatic forces. And now we think that this electron is put into motion by time harmonic applied field. So we excite the electron and atom by time harmonic applied field. And because the electron is having a so much smaller mass than the atom, what actually happens is that the atom is still, and only the electron starts oscillating because it's a charged particle and we are applying a time harmonic applied field. And now we want to describe the motion of the electron. And how do we do that? Well, we write a Newtonian mechanics equation of motion derived from the Newtonian mechanics, and essentially we end up mathematically with a linear differential equation of this form. So we have the mass of our electron, we have the second time derivative of the displacement of the electron, so x, two dots there signifying two time derivatives, and then we have a dampening term, so we have the mass of our electron times the damping term gamma times the first time derivative of the electron displacement x plus kx. So this is the kind of harmonic contribution arising from the fact that the electron is being bound to the nucleus, to the atom. So we have the K. This is the spring constant arising from the electrostatic forces that bind the electron to the atom. And then that's the kind of like a term that gives us a kind of like restoring force and puts the electron into an oscillatory motion and not a free motion as we have in the Drude model. And then we have the driving field. So we have the charge of our particle Q times E. So please remember Lorentz force. This is exactly that. But now we neglect the magnetic contribution and we assume that the driving field is a time harmonic oscillation. So it's of a form exponent I omega t. So simple linear differential equation, and we know how to solve this, and we have done this already before. M is the electron mass, gamma is the damping term, and K is the spring constant arising from the Coulomb force, and then Q is the charge of our electron. And X here gives us the displacement of the electron in terms of the equilibrium position. So when the driving field, the E field, is 0, then the electron will be in its equilibrium position, and the X equals 0 is that equilibrium position. And please note, this is a damped harmonic oscillator, so we have the dampening term here, and this corresponds to the fact that physically that if we have a driving field, it puts the electron into motion, and when we turn off the driving field, the incident electric field, this term ensures us that upon enough time has accumulated, then the electron stops being oscillating. So it doesn't just oscillate until the end of time. But if we would not have this dampening term there, then the electron would start oscillating until the end of time. And this is not very good in terms of kind of physical reality. Not to speak of the fact that we would never be able to kind of really excite the electron neither, because it would be so slow of a object. But okay. Solution to the differential equation, and I do not show it anymore like how it's done, but essentially we just place in a trial function for the X for the displacement of the electron that would be also of a time harmonic oscillation, and then we would get that the amplitude for the displacement would be of a form that it's the Q divided by M divided by omega naught. So this is the resonance frequency of our oscillator system arising from the stiffness of our potential well minus omega squared. So this omega is the driving field's frequency minus gamma I times omega. So this is the dampening term arising from the kind of dampening of our system. And then this is multiplying the incident field. And as we can see, the displacement, we have a frequency dependence in our displacement. So clearly, when the driving field's frequency, the angular frequency omega, approaches the resonance frequency of our material system, we have a strong peak arising in the displacement, so that the electron starts oscillating with a stronger and stronger amplitude. So a resonance takes place in the system, in the dynamics. And we can easily link this displacement to the material permittivity epsilon by just recalling that the material polarization, so the capital P, that can be also described that we have the kind of number density of dipole moments. And for this kind of oscillatory particle, which is charged, the electric dipole moment P, small p, can be described to be the charge of the particle times the displacement, so P equals Q times X. And now we have a relation for the material polarization in terms of these microscopic quantities of arising from the oscillator system. So now we can place in an equation from the above. So we have the P equals to N times Q squared divided by M, mass of our electron. And then we have in the denominator a term that depends on the resonance frequency omega naught of the oscillator of the incident driving fields frequency omega, and we have the dampening term there, I omega gamma. Sorry, I have a typo here. I should be gamma here and not just I omega. So this term, we have the fraction. We can write that must be equal to epsilon naught times material susceptibility chi, because remember, P can be also written to be epsilon naught, the vacuum permittivity, times the material susceptibility chi, times the driving field E. Now we have really a relation for the chi. And then recalling that the relative permittivity is of a form epsilon r is 1 plus material susceptibility chi, we can really write this equation for permittivity. And please, permittivity here, I'm now speaking of the absolute dielectric constant of the material. So this epsilon is actually the epsilon naught vacuum permittivity times the relative permittivity of the material system. So essentially here, what we have is that we have a relative permittivity here, and we have the actual absolute permittivity, the dielectric constant of the material. So we place this 1 plus chi here, and then the rest is history. So we have a form epsilon naught plus n times q squared divided by the mass of our electron m, and divided by omega naught squared minus omega squared minus I gamma omega. So this is what we have now for the permittivity. And likewise, we can write an equation for the refractive index n, just recalling what we have discovered already earlier. And remember that the refractive index, essentially, when we are thinking of non-magnetic materials, the refractive index is essentially the square root of the relative permittivity. So please remember that for most of the materials, especially when we are thinking of light matter interaction and optics, is that the magnetic permeability is weak. So mu is very close to the vacuum permeability. And this gives us the approximate relation for the refractive index. And now we have the dielectric constant, so we can now write the square of the refractive index by just as a1 plus this term we had found earlier. So please note, the main thing here is that the previous equation we had was for the dielectric constant for epsilon, and n squared is now in terms of the relative permittivity, so we need to divide the previous equation with the vacuum permittivity, so that's why we get the unity here, and that's why we're dividing here with epsilon naught. And now we have the frequency dependent refractive index, and especially this is a good equation when we are far away from resonances, because then we can effectively just describe many resonances using a single resonance, because only just one major contribution usually dictates most of the response. And then we could, for example, very easily describe the dipolar contributions to the molecular polarizability. So in essence, if you would be interested in some specific wavelength regime, we could very easily describe what is the dielectric constant of the material at radio and microwave regimes. So at the quite long wavelength regimes, so close to kind of like a conventional electronics. And of course, what we have described, the Lorentz model and the kind of like single damped harmonic oscillator, we can really easily also generalize this approach to visible wavelength regimes, and we could include also the electronic contributions into the piece of mathematics that we have described. And how we would do this is that we would just essentially start having several resonances in our system. So please note here, we only had a single oscillator, a single resonance that is associated with a given resonance frequency and a given dampening term. But we could just start summing over many resonances, and then we could have a kind of like a effective index arising from many resonances. And this is what we will briefly do next in the kind of final slide we have for the lecture. So damped harmonic oscillator model that we have just described, we can generalize that to many different uncoupled harmonic oscillators, and this results in a relation that we have the refractive index squared is of a form 1 plus n times q squared divided by epsilon naught m. And now we sum over many resonances. So we sum over L resonances, where we have now on a mj here, a kind of like oscillator strength term in denominator, and in the denominator we have a frequency dependence. So we have the kind of like specific frequency associated with the jth resonance or transition. we have the frequency of the driving field, and then we have a similar dampening term where the gamma j now depends on the kind of given transition. So what is the lifetime associated with a given kind of excitation or transition? So J labels resonances or transitions that may take place in our system. So these we could, for example, put in phonon excitations, phonon transitions, and we could excite also electronic transitions. So we should sum over different contributions. And then these MJs would be the kind of terms that would tell us what is the oscillator strength that is associated with the given transition. So basically it would tell us how probable it is that when we shine incident electromagnetic radiation in our solid, how probable it is that the given transition would take place. Let it be electronic transition, or let it be a phonon transitions that we are actually exciting, for example, an optical phonon or acoustic phonon in our system. These oscillator strength terms here would tell us how probable it is that this transition will take place. And subsequently, we see here that depending on what kind of transitions we may have, that will have its effect on the refractive index and its frequency dependence. And note here, we have uncoupled oscillators, so they are kind of individual oscillators. So this is, of course, sometimes a little bit silly approximation to make, because we see, especially when we had described things, the phonon dispersion relations and the kind of electronic band structure, we know that the periodicity of our substance, it should actually also matter to the optical responses. And here we are not essentially doing much in terms of that. What happens is that the most of the time, we don't really need to consider a fact that we would have coupled oscillators, so that most of the time we don't need to consider those. But admittedly, if we would be interested in semiconductor optics, so essentially we would be doing experiments at the longer wavelengths, and we would be exciting phonons in our systems, then you probably would end up needing a kind of n-coupled harmonic oscillator systems to describe your refractive index of your semiconducting substance. But then you would be more interested in semiconductor optics, semiconductor physics, and then you would be needing to generalize this. And needless to say, then you would also have a dispersion relation being formed for the refractive index profile. So that the same kind of physics, of course, would happen also in terms of light-matter interaction that we have realized to take place with phonons and with electronic transitions. But if you're interested, there's a very good book from Klingshirn called, if I remember correctly, Semiconductor Optics, or maybe Introduction to the Semiconductor Optics. But there the mathematics is being derived, where you would have actually n-coupled harmonic oscillators giving rise to your frequency-dependent refractive index profile. But that's way beyond our scope here, so I do not speak more of that. So the equation that we see here, this is known as the Helmholtz-Ketteler formula, and this can actually give a very good agreement with dielectric materials and their refractive index profiles. And the why that is so is that we actually can have many resonances, and these affect the refractive index profiles, and this gives us a very good predictive power. And what we will do next, in the next lecture, we want to kind of try to elucidate to you what are the quantum mechanical origins and what is the motivation on this form, functional form for the equation. So essentially we would try to elucidate to you that this actually makes sense also from the quantum mechanics point of view, that we have this kind of equation. And then we would also qualitatively describe to you how we could calculate these parameters that describe and are being used in the Helmholtz-Ketteler formula. So what are these MJs, omega naught Js, and gamma Js? So what kind of resonances we may have in our system, and what are the things that affect these parameters. But more on that, of course, in the upcoming lecture on the actual topic. So I thank you for listening this lecture, and please join me in the upcoming lecture. Thanks and bye-bye.